Okay, so our last speaker today is Balaji, and the title is not in the board completely.
No. The title, this is a fuzzy title.
Okay.
I wanted to retain Narasimhan from Thomas, and I had given a title called Deformations of Stacks, which is, I start with a disclaimer. I have no precious little about deformations of stacks. So it's more like on a theorem of Narasimhan Ramanujan on deformations.
Okay.
So let me begin by thanking Oscar and Pranav for showing a lot of patience and inviting me to give a talk here. So this is a joint work with my younger colleague, Yashonidhi Pandey. Mic is not functioning? Is it not working? Where? My voice? No. No, I mean, I might sing a Hindustani piece. That's good. Okay. Yeah, thank you. So, as I said, my title of the talk is, I don't know, I must have been in some other state when I made that statement. So I just want to make the following computations here. I also found a Hogoromo. Yeah. So aim is, so let M S denote, let M denote. So let me start with, as always, K algebraically closed. G almost simple. Simple, simply connected. Okay. X smooth. Projective. Okay. And I'll have notation M, which is MXG, which is, I'll just call it M, which is also called 1XG. And I'll denote by M, MS, the open substack of stable principal G bundles on X. So let E be the universal G bundle. And so here, the Lie algebra, and I'm interested in the following vector bundle. So I take EG, the associated vibration, and I restrict my attention to MS, and I take the projection, I'll call it Q, and I'm interested in the following object. I define R1 Q lower star of EG, and I denote this by TM. That's a notation. And I denote by omega. The dual of this vector bundle, the stack. And I'm interested in AMS compute So this is. Yes. And then, because I'm working with a stable stack, I'll draw some conclusions for the core space. So this is the goal. So this origin of this kind of questions goes back to a classic paper of Narasimhan and Ramanujan. So this is the paper. My OneNote copy here. So this is way back in 1975. So, I mean, since it's quite ancient now, let me just recall what they do. So, well, they work with the moduli space of Rankine fixed determinant. So xi such that the GCD of n and degree xi is 1. So they just look at this moduli space. So here stable is equal to semi-stable. Okay, so smooth projective variety. So this maybe I should just denote it by a straight tab. So this is moduli space. So they prove these theorems. So they show that hi of mxs and xi p m 0 pi not equal to 1. And this is in fact isomorphic. I mean, this is, sorry, move on. H1 of x dx. They also compute the cotangent cohomology. So this, once this is done, this can be interpreted as showing the infinitesimal Torelli theorem also. So the Torelli theorem was already known at that time. Mumford, Newstead had proved it. And they did it for higher rank, the same proof. But this also computes the derivative of the natural map. You might say x goes to mx. And this result proves that this association is also, in some sense, differentially injective. So this is like an infinitesimal Torelli theorem. So this also computes, because it's a smooth projective variety, the deformations of the moduli space. So, and the main tool or technique is the following. So this type term called Hecker correspondence, see, pardon? Genus?
Yes.
At least 2, maybe. I will eventually require 4. Huh? This is okay. This is no. I think this is, even here they assume at least 3. So yeah, I forgot to say that. So the key tool is something called Hecker correspondence, which has a different interpretation in different schools. So what they talk about here is the following object. So they set up the following correspondence. Let me write like this: M N O. This is moduli space of Rankine trivial determinant bundles. And then they go to some space, let me just call it H here, and to Mn xi. Okay. These are all core spaces. So I don't know. Sorry, I think this is. So this Hecker correspondence is constructed in the following manner. You take a vector bundle of rank n here, and if you want a suitable degree there, you take a parabolic structure. So you fix the point x in the curve x, and you fix a parabolic structure of a suitable. So if this is of degree d, and I think of that subspace of dimension d inside this, and look at the torsion sheaf Tx, which is Bx mod Wx at the point x and 0 elsewhere, and you take the kernel of B prime, and so the set of parabolic bundles H will be the moduli space of parabolic bundles with this quasi-parabolic structure. And assume weights, small weights. So you get a projective variety, and so the correspondence then looks at such a parabolic structure. Let me just call this V comma delta here. So this is delta together with some weights, and I associate to V the object V prime here, and it takes a little effort to prove that this actually turns out to be stable or semi-stable, as the case may be. So I'm not assuming that this is co-prime right now, but more generally. So if you assume that this is rank and degree here are co-prime, then V prime automatically will be stable, and you'll get a morphism here. And in that case, this part of the map, so let me just call this H and pi, for reasons which we'll see later. So when degree of xi and then the GCD is 1, I mean, one may identify the moduli space H with the projectivization of F sub x star, where F is the universal bundle on M and xi. Notice that in this case, where the rank and degree are co-prime, it's a fine moduli space, and you have a universal bundle, and you can take the universal bundle here and restrict it to the fixed base point x, take the dual and take the projectivization, then you can identify this with the Hecker space H. So this is what they call Hecker correspondence, and the key result that they prove is that I mean, this they restricted to, so I look at H S to MS here, this to M and xi. So wherever it is defined, they show that TH is let's TH be the relative tangent sheaf, tangent model here, and this is T pi on this side. So they show that TH is isomorphic to T pi star. That's where wherever it's defined. I mean, I'm looking at the stable locus here. So this, once it's proven, then they can use some nice geometry about projective bundles or Grassmann bundles and recover the theorem. I mean, I have to be a little careful. I think maybe here I'm automatically assuming that this degree is 1, not just coprime. So in which case, both sides will be projective bundles, and in that case, they're able to prove this. So they compute the cohomology of the tangent bundle on the moduli space using this as the main tool. I'll indicate how they do it towards the end, but the key central feature of the proof is this fact that they are able to prove, and using this and certain basic statements which I'll state for more general cases, one can then use this fact together with some generality to get the cohomology of the tangent bundle. Okay. Pardon, H is moduli space of parabolic bundles at a marked point X. That's right. That's right. So it will be a projective bundle only on some stable parts, and because you're looking at semi-stable parabolic bundles, it won't be a full projective bundle. So you'll have to look at, when I'm making that statement, you have to be a little careful because you're taking the inverse image of the stable bundles here on one side, and then you're looking at the full space on that side. So you'll have to make the comparison on a certain set. Because all this is happening at the level of core spaces. Okay, so I think I can erase this. So my goal is to make these computations on the moduli stack of stable G torsors on X. And as one can expect, one needs, when I stated that fact just for this purpose, one needs a natural generalization of the concept of a Hecker correspondence there. And one has to build the right Hecker correspondence and make some computations of this kind. Okay, so let me, so I work with X, and I also fix a base point X. Okay, so I want to set up, the first thing I want to do is set up a suitable Hecker correspondence in the setting of script M, which is Balaji. For the moment, I'm not assuming any stability conditions, and when I want to make the computations, I'll make the stability assumptions and genus assumptions so that I can have some large codimension property. So what is the Hecker correspondence? To do that, I make some root theoretic statements here. So let S be the set of, I'm saying that I fix a root system. So I fix a maximal torus, a Borel inside the group G, and I fix, let phi be a set of roots associated to T here, and let S be the set of simple roots. And so once I have a set of simple roots, I can talk about positive roots and negative roots here, which are positive Z linear combinations of S. And then the key thing which one has to keep in mind now is what's called the highest root. So the highest root can be defined by taking the adjoint representation and taking the highest weight. Okay, so this is a well-defined thing. So this will be some C alpha, where alpha runs over S, and these are all positive. And it's a genuine highest root in the sense that all the coefficients are larger than or equal to all the other positive roots. And there's one denotes by alpha naught minus of alpha max. Okay. Now, to the set of simple roots, so for every alpha in S, I can associate there exists a maximal parabolic subgroup denoted by P alpha inside G. This, in some sense, is you take the Dinkin diagram for G, then the semisimal part of the Levy there is given by all the simple roots which are not equal to alpha. I mean, you throw out alpha and get the maximal parabolic. That's the convention. So let me now define the concept of a parahoric group. So to do the Hecke correspondence in this setting, okay, I need to interpret this moduli space of vector bundles with rank and degree co-prime as a parahoric moduli space. So what does one do? So there's a general, so there is a unifying theory, which is one can talk about parabolic bundles and the co-prime moduli spaces all in the language of parahoric groups, especially if you work with a general G. So what does one do? So, so you work with, you have this Riemann surface X, and you have this marked point X. So you fix an analytic disk or a formal disk, and you do the following. So let this be spec A, where A is a R series ring in one variable, and spec K be the open subset here, which is corresponds to the function field here. So the parahoric groups is an affine analog of a parabolic subgroup here. And these are the following objects that I'm looking at. So I'm interested in the following group, G capital K, which is the formal loop group associated to the function field here. And I'm interested in subgroups here, which are called bounded, in the sense that the order of poles is bounded for the elements here. So this is the concept of a bounded subgroup. So the example of a bounded subgroup is you take the A-valued points of the group. So this is an example of a bounded subgroup. This is in fact an example of what is called a maximal bounded subgroup. And there are other natural bounded subgroups which come here. So you take the evaluation map from the A-valued points of G. So when I write this, I mean morphisms from spec A to G. So I can evaluate the uniformizer T goes to 0 here. So then I have subgroups, the Borel, which I've already fixed. So I can take the inverse image of the Borel subgroup. So I can take the inverse image, B, and I denote this by I, a subgroup of GA inside GK. And this I is called the standard Ivahori. Subgroup. Standard because I fixed the Borel for my root system, and an Ivahori in general is a GK conjugate I. So that's the definition of an Ivahori, and a parahoric subgroup of G A is a subgroup which contains an Ivahori. Okay, so this is an exact analogy with parabolic subgroups here. These are parabolic subgroups which contain the Borel subgroup here. So we have the affine analog of a Borel, which is the Ivahori, and we take its conjugates, like in the usual case, and then a parahoric subgroup of this group GK is something which contains an Ivahori. So that's a parahoric subgroup. And in the case that I'm working with some simple, simply connected groups, parahoric subgroups up to conjugacy by GK are indexed by the affine simple roots. So this is a fact. So there is, to be able to talk in detail about all that will take me some time. So let me just denote the so-called affine simple roots by theta alpha. And these are, if the rank of my group G is L, so I fix my group G, and rank is the dimension of the maximal torus here. If it is L, then these affine simple roots are L plus 1 in number. And of them, one of them corresponds to the root alpha naught, which I chose. Okay, so there is alpha naught, which corresponds to, in some sense, the so-called origin of the fundamental alcove, and there are other affine simple roots indexed by the other simple roots. So there are L plus 1 of them. And yes. Pardon? Sorry? No, I didn't get your question.
They are bounded.
These are bounded subgroups. And this is a bounded subgroup. The Ivahori is a bounded subgroup. In fact, you know exactly how the picture looks like. So in some sense, you have if you think of the upper triangular matrices, then I want the positive powers of T on this side. So these parahorics are all bounded subgroups, but they have a more important property, which I just want to tell now. So as I said, there are so many parahorics now, and there are nice relationships between the bounded subgroups. So let me denote the parahoric associated to is theta alpha, p theta alpha, and one can define. So this, I don't know, maybe I should define it as this inside GK, and this can be explicitly described in terms of generators So I take my maximal torus, look at the A-valued points, and take all the root groups UR, and I associate the e to the power. So, so I need to have my notation for that. So I define it as T to the MR theta alpha A R and P. So these are some sort of generating sets, and the MR theta is minus of and this is the standard pairing. So this is R comma theta. So you have these parahoric subgroups here, and the basic theorem of Bro-Hurwitz classifies. So the theorem of Bro-Hurwitz is that these groups are schematic, i.e., there exists affine connected group schemes G theta alpha on spec A, such that G theta alpha restricted to spec A is G cross spec A, and G theta alpha of A is P theta alpha. Means, so this in some sense also is precisely the point of being bounded there, that it's in fact the A-valued points of a smooth group scheme. So I should have said smooth, fine, smooth, connected. And there is a relationship between, so among these parahorics, I said that I take the inverse image of the Borel here. I can also take parabolic subgroup P alpha that I defined earlier, and I can take the inverse image, yeah, of P alpha. So that is so let me write. So this I can define it as script P alpha parahoric subgroup given by, so this is called a standard parahoric. Okay. And the remark is that even if P alpha is a maximal parabolic subgroup of G, this parahoric is not a maximal parahoric. So there has to be careful about the notions of maximal parahorics here. So I said, only the maximal parahorics, not all the parahorics. Okay. And there is a relationship between this parahoric and the ones coming from there. So P theta alpha, P alpha of K is in fact P theta alpha of K intersecting. Okay. So once this notion of a parahoric group scheme makes sense, then one can talk about the following object now. You have taken this curve X here. You take this point and take the disk, which is a spec A. So take the standard, take the X minus the point X here, and here take, for example, the trivial group scheme G cross X minus X, and on spec A, you take a parahoric group scheme coming from, say, the maximal parahorics G theta alpha, and then glue them by some gluing function along spec K. I mean, the gluing has to be done carefully, the algebra geometric setting. And then what you get is a global parahoric group scheme. On X. And for such X, for such G, I mean, you can simply call this big group scheme as G theta alpha X, the whole of X, with some choice of gluings here. So then there is theorem of Heinloth, which shows that the stack of such group schemes, or even more general ones, is an algebraic stack. Okay, so I needed all this to be able to talk about the Hecker correspondence. Any questions up to now? Or is it, or last lecture, is it more boring than what one wanted? Any questions? No? Okay, fine, good. That means everything is clear. Okay, good. So what I want to do is set up the Hecker correspondence between M G, which is just bun G. Let me just call it bun G. Bun X G alpha, which corresponds to the parahoric alpha without a theta in it. And on this side, bun X G theta alpha. So this map I'll call H. This is. So I call this map H because some of these maximal parahorics that we are talking about here, these group schemes that we have discussed here, that is G theta alpha on spec K, are reductive when theta alpha are what are called hyperspecial. So among the simple roots, depending on the type of the group that we are looking at, the group scheme, parahoric group scheme, can actually be a reductive group scheme. And those are special or hyperspecial vertices, I'll just call them that. And one can then have a classification of what these are. And so, and we want to understand what these maps are. And these maps are quite interesting, actually. So the first observation that which one has to make here is that these group schemes, how much time have I?
That's wrong.
Okay. Okay. So I want to say that these group schemes are not reductive, but if you look at the closed fiber, there's a full description of the closed fiber, and if you take there is a natural unipotent radical in the case when it's not reductive, and then you can take the reductive quotient of this, and the root system for the corresponding derived group can be written down purely in terms of the standard Dinkin diagram. And the most important thing here is that pardon?
Very hard to see.
Very hard to see?
Yeah.
No. So I've written that there is a reductive quotient here for the closed fiber. Reductive.
You're not assuming hyperspecial.
I'm not assuming hyperspecial. So if it's hyperspecial, I don't have to talk about it. But so I'm just saying that I want to understand what these maps look like. So since it's hyperspecial here, so I just want to make a small definition here. There's something called the neuron dilatation. So you take a group scheme on spec K and take the closed fiber GK and take a subgroup HK inside this closed fiber, then one can construct this and a different model for this group scheme, which is usually denoted by GHK on spec K, which has a property that there's a morphism from this to spec K, and this group scheme GHK on capital K is isomorphic to GK, and at the closed fiber, GKHK actually maps to HK inside GK. And this is universal with respect to this property. So it's constructed as some sort of an affine blow-up of this group scheme G. So such a group scheme is there. And what one can prove is that it's not very hard to check that G alpha, in fact, is take the standard group scheme GA and take the parabolic P alpha in the closed fiber and take the neuron blow up of that is this group scheme. And the same group scheme can be realized from a neuron blow up of the parahoric G theta alpha by a subgroup. I'll just call it P theta alpha K, which is a subgroup in the closed fiber, reductive subgroup. There is a parabolic subgroup here in the closed fiber, and you can take the inverse image of this inside this big closed fiber. I'll call it P theta alpha bar, and you take the neuron blow up of this. So once you have a neuron blow up of a subgroup, torsors under this by extension of structure group will give you torsors here. And this can also be seen by the fact that these parahorics, the way I've defined the parahoric property there, the sections of this group scheme will go into the sections of this group scheme and here. And therefore, you'll get the extension of structure group maps. But the more important thing is to realize that pi is a G theta alpha K mod P theta alpha K fibration bundle, and H is a G mod P alpha bundle. So that's the key property, that you can have a Hecker correspondence in which either side is a homogeneous space. Question? You take any group scheme G on spec K, flat, smooth. Take the closed fiber GK and take a subgroup HK. You can construct a neuron blow up of this group scheme along the subgroup HK in the closed fiber. So you'll get a new model for G capital K. And there is a morphism from this model to this model. The morphism factors at the closed fiber through the subgroup HK. And this is universal with respect to this property. This is called the neuron dilatation. So in this diagram, this group scheme, the standard parahoric group scheme can be thought of. So this one is a fibration with fiber G mod P alpha. And this one, you take the closed fiber of this group scheme, take the reductive part there. There's a natural parabolic subgroup there, just defined by the theta alpha there. Simple root alpha inside the closed fiber. You can look at the root system of the reductive part of the closed fiber. There'll be a maximal parabolic there. You can take the inverse image of that in the closed fiber and construct the neuron blow up of that. That also is precisely G alpha, isomorphic. So this side, the fiber will be the homogeneous space given by that parabolic. So I'm saying G alpha is a parahoric associated to the standard parabolic subgroup. So if you take the inverse image of P alpha, like the Borel, then you get a parahoric subgroup which is sitting inside GA. So it has a It's like you get a subgroup scheme of the standard hyperspecial group scheme GA from these simple roots. That is a different maximal parahoric group scheme. No, the closed fiber need not be reductive. That's the key point. I mean, it could be reductive, need not be reductive in general. So the ones for which it is reductive is what I call hyperspecial. In the case of SLN, all of them will be hyperspecial. Yeah, but for example, G2, there's only one hyperspecial. So you have this kind of nice picture here, right? I told about this because you can then analyze the fibers here, and this is like a G-mod P fibration. Okay. With this property now, I'm claiming the following. The theorem that one proves is the following. One can then prove that TH is isomorphic to T pi into 1. And this is, of course, in case 1, if there exists a second hyperspecial. So this is all cases where G is not equal to G2, F4, and E8. The second case is when G equal to G2, F4, and E8. Yeah, the group scheme G alpha, for which this is coming from the parahoric subgroup given by the parabolic subgroup G. So this one is the neuron blow up or the neuron dilatation of the parahoric group scheme G theta alpha along a certain subgroup in the closed fiber. No, this is the notation. This is a notation. It's not my notation, it is Renault's notation. I can't. I mean, this is in the paper of Anantaraman. These notations are given. So I'm just following the pattern. So you can realize this standard parahoric from the hyperspecial as well as any other maximal parahoric. I mean, not any other, this maximal parahoric, the one given by the same theta alpha. But in the case when G is G2, F4, or E8, we don't have this extra hyperspecial to play with. In that case, what one does is you take the affine Dinkin diagram. So you'll have an alpha naught here. And in the Dinkin diagram, there will be a simple root alpha adjacent to alpha naught. Okay, so what one looks at is this part of the Hecke correspondence now. So you take bun G on this side, and you take bun X G alpha, and on this side, you take the bun X G theta alpha corresponding to this simple root, the maximal parahoric correspondent. And what one proves is that this fiber, in this case, is actually SL2 of alpha max modulo the Borel here. So it's a P1 fibration. And in this case, of course, it's the same. Okay. So here one doesn't show something like this, but using this, one can prove the following theorem. So the main goal is to prove the following. One can prove in both cases that Hi of M alpha, so M alpha is G alpha, TH is isomorphic to Hi minus 1 of M theta alpha O. So this is the main goal. So once this is done, one can then use standard Leray spectral sequence theory in computing. So in both cases, whether it is the case when you have a center or not, this theorem always follows. To make this computation, I'm saying that I look at this Hecke correspondence picture here. I have the relative tangent sheaf TH here. I'm interested in computing the cohomology of that. So why do I need this? So let me state the basic classical fact due to maybe several people, I don't know, it's well known maybe. Yeah. So take F, take a principal G bundle. So E is a principal G bundle on P, and P is a parabolic. So take this map fibration and look at the relative tangent sheaf TF and its dual TF star. So then you have the following theorem. Ri F lower star of TF is EG for I equal to 0 and 0 otherwise, and Ri F lower star of TF star is OX to the L for I equal to 1 and 0, I not equal to 1, where L where L is the number of while group elements, W of length 1, such that for every beta in S minus alpha, or this alpha that take I. So let P be given by a subset I of S. These are the complement of the simple roots that I omit for this. For example, if I take P alpha, then I is S minus alpha. So for every beta in I want W beta to be a positive root. So this L is the number of while group elements of length 1, such that for every beta in the subset I, so I corresponds to the parabolic P, W beta should also be a positive root. So in the case, so with this computation now, you can apply this to both sides of the Hecke correspondence. So here you would have realized TH is T pi star. So I use both sides correspondence and make the computation. Then one can then prove that HI of the tangent sheaf. The final theorem is for stable bundles. HI of XTX is isomorphic to HI of MS TM for I equal to 0, 1. So this is the main theorem. Once this Hecke correspondence is understood correctly and these computations are made in terms of the tangent sheaf, and once this is proven, the rest is simple application of Leray spectral sequence. So the key, or the only thing that is a takeaway, is that the Hecke correspondence contains this information, which is that if you choose, you start with the hyperspecial G, you can flip around and prove the whole thing. So the remark is that if you take the group SLN and you choose the coprime moduli space, that's one of these maximal parahoric moduli spaces. So you'll get, you can, whatever game I have played with T pi and TH, you can play with TH and T pi, and you can compute the deformations on this side. Here stable equal to semi-stable, so that will be a gerb over the moduli, coarse moduli, and you can compute the Narasimhan-Ramanujan theorem as a consequence of this. Because in that case, this moduli space will be stable equal to semi-stable, and you'll have the coarse moduli thing will be a projective variety, and you can come down and compute the tangent. So you'll get back the old theorem. I think I've done.
Yeah, so just to clarify the theorem, on the right-hand side, that's the cohomology of the universal adjoint bundle, right?
This is the P lower star of E add.
First cohomology. So, oh, no.
This vector bundle is P lower star of, or Q lower star.
Yeah, but
of E over this.
Q lower star, but it's not R1 Q lower star? No. Oh.
R1 Q lower star, sorry.
R1, right,
Yeah.
right. So it's first cohomology then. And But on the left-hand side, that's T, is that Tx?
A tangent.
Tangent.
Yeah, so X has no automorphism, so H0 is 0. And higher cohomology is H2 onwards 0 because X is a curve. H1x dx is 3g minus 3 in this case. So, and this side, this is precisely the tangent sheaf for MS because there are no automorphisms. So H1 is constant dimension there. So you will have a vector bundle in this case. And this is the analog of, so once I know this computation now, and I can go down to the core space and compute it. If it's a gerb.
So you said you're always working with stable bundles, right?
I'm looking at MS for the stack, always.
So
So
there
that
could be
statement,
some strictly semi-stables.
pardon?
There could be strictly semi-stable bundles.
Of course. That's why this is not a vector bundle. It's TM that I've written down. You could have automorphisms. So H0 and, I can't use semi-continuity theorem because I don't have the constancy of dimension of H0. So that's why I restricted myself to MS. And I'm looking at X cross M to M, the projection.
So the cohomology on the total, like MSS, that could be different.
Pardon?
The cohomology, if you consider the sheaf
Yeah.
on MSS.
No. If
Could be
you
different.
extend the sheaf, then there'll be no difference in the cohomology.
All right. Okay.
Because that's some hard talks. You have, if your genus is sufficiently large, you can do that. That's not a problem.
Thank you.
No, I didn't mean that. Yeah. So I'm saying that by the way, I want to say that when I sent this manuscript to Telemann, he tells me it's a trivial corollary of 2 or 3 of his papers. One, and he told me so that because this this cohomology can be proven by Hitchens' approach also, because there's a consequence of Hitchens' theorem, and Telemann generalized this more generally for the G stack. So he computes not only the cohomology of the tangent sheaf but the symmetric powers also. So that's a much larger thing, and perhaps the slight difference here is that I can do characteristic P also. It's not a problem. And also one can do parahoric torsors also, because when you take parahoric torsors, the Hecke correspondence that I'll be doing is at other points, not at the where it's already G. And then the same thing works. That's what I've written in the paper. So one can, I'm saying that the methods here are relatively simple compared to what Telemann is using, because there are 3 papers of his, that he quoted something with Gronowski, somebody, it's Nippon paper, 2 papers Borrell bought of his. Of course, I don't remember the name.
Yes. Yeah. So what
There is an isomorphism of the cohomologies.
That's HI minus.
Huh? The relative tangent sheaf on M alpha.
Yeah.
And the O, standard O on M theta alpha.
Yeah, I was confused about that M.
This is the stack.
HI minus.
This is the stack. Huh? This is I minus 1.
Yeah, I meant 1, but then the M.
It's cohomology. Okay,
this is H.
Yeah. So, can you say a few words? Where do you use this isomorphism in the proof?
You have to read. It's not very difficult. It's standard Leray spectral sequence. Once this is done, it's what I'm trying to say is that I'm putting many things under the carpet, so you'll have to do some work for that. I just was trying to stress the key point. It's not completely trivial. Yes. Carlos is asking something. Yes.
As you were just saying, suppose you do parahoric structures at several different points. Does the moduli space depend, because isn't there a parameter that tells you how the different parabolic subgroups fit together as you go from one point to the other? I mean, you're taking the constant group scheme G, then you're looking at parabolic subgroups at the different points.
That's right.
But there's a choice of, up to conjugacy at each point.
Of course.
And when it's just one point, maybe that doesn't matter. But if there's several points, you could sort of move the conjugacy classes of the parabolic subgroups
Yes.
different ways. Does that change the moduli stack?
Moduli stack won't change. You
The-
mean,
the
even if so I think, see, the gluings don't matter. And what do you mean by,
Well, I
if
don't
you
know.
choose several parahoric structures, you'll get a parahoric moduli space. And you mean?
Will those stacks be isomorphic? If
I think that's correct. Jochen.
if you
change the
if you change so when you define the script G, you have to choose a parabolic subgroup or some other subgroup at each point, if you have several different points. So you choose a subgroup, you choose a quotient thing or whatever, subgroup scheme at each point. But you can modify those by conjugacy at each point individually,
Yes.
but which might not be globally conjugate.
Yeah, but it's an inner form. So Torsors under this isomorph, the stacks will be the same.
Is
It
there-
depends.
Can you write down explicitly the isomorphism?
Yes, I think so. I think one arises as the automorphism group of a different bundle in the same stack. I think it, yeah.
Oh,
Yeah. Okay.
okay.
As it says. Yeah, there's a question here.
So in the first case, the thing on the left of the Hegel correspondence can also be seen as
Parahoric.
yeah, but they can also be seen as bundles on the Stucky curve, right? Like
Of
the
course.
so can all these parahorics be seen also as bundles on Stucky?
That's my theorem with Seshadri.
Oh yeah.
There are more questions? Okay, then let's thank Balaji again.